Hi, friend. Today we're doing something a bit different. Maybe not everyone knows it, but I actually got my degree in physics. So I feel like uh, I'm a bit qualified to talk about all of this stuff. And few friends just asked me, "What do you think about those nuclear fusion news?" And I was like, "I don't care. It's probably nothing." And then it turns out that uh, everyone is freaking out and made like a clickbait, I guess, titles about it and stuff. So I decided to look a bit more. So I followed this channel by Rebecca Watson. I don't remember what exactly I started watching from her. I think it was kind of like politics and general. I don't remember like COVID stuff or something like that. So here's the thing. Basically, like scientists will. There was a sketch by someone about this, but I don't remember now. But basically, like scientists would say something like completely reasonable, and journalists will try to make it into. I don't remember what it was like. Uh, Maybe scientists found like a trace amounts of water, and like all the headlines are like, scientists are sure that there is life on Mars, something like that. So and so what happened is that uh, basically they overblown it out of proportion. And Rebecca recorded a video where she's like, "Hey, I think this is doesn't make sense." But when she was doing that, she actually made few mistakes. And I looked through her comments, and it doesn't look like people in comments kind of like caught her in this mistake. So I don't know how long I'm going to make this video, but I want to just kind of like react to it and say what she got right and what she got wrong. I was thinking like how much should I research, how much kind of like deep I want to go into it, and I wasn't like a nuclear scientist, so I feel like if I'm going too deep, I will probably start making my own mistakes. So I will probably keep it kind of like surface level so that everyone can understand. And hopefully, she can watch this video and kind of like may make some corrections and stuff. I will just start like reacting through kind of like the whole video. I will cut out parts that don't make sense, or maybe like I didn't find anything to react to, but I will try to do it kind of like throughout the whole her whole video.
And oh my God, did you guys hear the news? Breakthrough in nuclear fusion could mean near limitless energy, reports the well respected Guardian newspaper this week. Researchers managed to release more energy than they put in, a positive gain known as ignition. Holy crap, that's incredible. I mean, that's literally incredible in that it's unbelievable. It is not credible. I do not believe it.
So I think that like so far is like her point is that journalists who are talking about this have no idea what they're talking about. But when she tries to put this into light of like scientists don't know what they're talking about, that's kind of like where I disagree.
Um, okay. Let me start by saying that I am not, this might shock you, I am not a nuclear physicist. In fact, I'm not any kind of physicist at all. I took calculus my senior year of high school, and I don't remember a thing about it. I think I got a B minus, maybe. I also got what I suspect is the only Bachelor of Science degree in the United States that does not require graduates to take a single college level math course. So
Yeah, so this is important qualification of her. Like, hey, I'm not a physicist, so don't don't take this too seriously. Uh, and I would, except that she tried to explain her point through physics, and I think that's kind of like where where she made a mistake. But again, I don't think that it's like kind of like too wrong, but it's just it's like two wrongs don't make a right. So it's like if journalists were wrong and she's wrong in trying to correct the journalists, that's still wrong. And that's why I'm doing this video.
Go ahead, look back through the past 10, 15 years of videos I've made for this channel. I challenge you to find 3 that deal with high level physics or math. The reason you won't is because I know when I'm out of my depth. I do not swim in the deep end of rocket science. I happily float over here in the soothing hot tub of biology and psychology and things that I'm comfortable with. But here's something I do know a little bit about. Free energy. Free energy is the idea that you can somehow get more energy out of a system than what you put in. And it has long been considered the magical key to a future utopia where we are no longer reliant on fossil fuels, where we don't need to release carbon into the atmosphere, where we can easily send spaceships to explore the farthest reaches of our galaxy. It's also long been a big old scam.
Yeah, so this is the first point where I think she just got it wrong. She tries to connect system like getting more energy out of it than you put in, and she's trying to connect that to free energy, which is, yeah, as she said, kind of like long-standing scam of like, hey, here is a perpetual motion machine, right? So we can only you only need to like start it once and it will work forever. And I don't know how she got into that. I think just the headlines of like, hey, they got more energy out of the energy they put in. It sounds in a way kind of like similar to free energy, but I still have no idea how she how she connected that.
For as long as I have been critically evaluating extraordinary claims, I've seen a new invention pop up at least every few years that claims to violate the laws of physics.
Yeah, so 2 points about this. They don't claim to violate the laws of physics. That's kind of like what should have put her off of this idea that this is somehow like a free energy. And the second one is like, yeah, every few years it shows up. It's like the nuclear fusion was theorized, I don't know, like 70 years ago or so. It's really long standing theory and kind of like engineering challenge. So to say that it's like, hey, this is just another scam of trying to trying to create a free energy, I just have no idea how that's connected. If it's a field that was I forget like when was the first tokamaks kind of like experiment like started, like 40 years ago or so. It's like it's not it's not like this is like a new invention as like, hey, this is a super machine that does everything. It's like a long-standing field on the par of, I don't know, better rocket science that she said, right? So I kind of like don't get this. I don't get how this got into the same category of all of these scams. Okay, I think I got like 10 minutes out of like 2 minutes that she talked.
Stern was an early example. Stern, I don't remember how to pronounce it. They were a company that in 2006 claimed that they'd created a machine that offered free, clean, constant energy. They were so sure that they had done this that they took out an ad in The Economist inviting scientists to test this device. Hundreds of scientists responded. The company chose a jury from amongst those scientists. They tested it and they found Stern's attempts to demonstrate the claim have not shown the production of energy. The jury is therefore ceasing work. Oops. It sounds to me like Stern truly believed that they had invented free energy. And there are a lot of engineers, amateur physicists that over the years who have fooled themselves. But it's a scam. And so there are also plenty of people over the years who have used the idea of free energy to separate people and businesses and governments from their money. Like Josef Papp, he was an interesting character back in the 60s. He claimed to have invented a car engine that could operate without gas for 6 months before needing to come back to the company to be recharged somehow. Richard Feynman wanted to see it work, so he went to a live demonstration where, according to Feynman, at the demonstration, the machine, which he says was obviously an electric motor on a battery, exploded and killed one observer and injured two others, though we kind of only have Feynman's word on that. But Papp accused Feynman of purposely destroying the engine, and he tried to sue Feynman, and Caltech ended up settling with him out of court. Papp went on to continue collecting money from investors, but he would never show another of his magical engines again.
Right. So I think your point here is that people will show some prototype and say, hey, give me money. I will give you like this unreal return, right? And she tries to put nuclear fusion into that category, which is like wrong just on the principle, because as I said, it's not a free energy device. So I don't see anyone trying to say that nuclear fusion is free energy device and it has unreal returns. It has pretty kind of like practical returns. So the main idea is that the fuel that it's going to use is pretty abundant. So it's not like getting energy out of thin air, but it's like getting it from heavy water, which is pretty easy to get by compared to like uranium or all of that kind of like nuclear fission fuel. So I don't want to say that this is like done in bad faith, but it's just her examples like are good, but I wish they weren't used in this context.
Yeah. What I'm saying is that while I may not be a nuclear physicist, I do know you can't get something for nothing. Yes, I know physicists have been working on fusion for quite some time now. And I know that this Guardian headline would be the greatest possible result of that work. But I also know that we are nowhere near that point right now. So what's really going on? Like this is a real newspaper, not the Daily Fail. Like they're not out there promoting an obvious scam. So what's happening? So this news all stems from the National Ignition Facility, NIF, at Lawrence Livermore National Laboratory right here in the Bay Area. They've been studying fusion, which is the way that our sun makes energy. As They Might Be Giants once told us, the sun is a miasma of incandescent plasma where hydrogen is fused into helium to produce a massive amount of energy, which we see as light and feel as heat. It would be great to be able to do that.
I mean, I don't know if I should go into into correcting all of this that energy that we see as light and we feel as heat. It's kind of like wrong on several levels, but in practical terms, that's kind of like close enough. So I don't know if I should correct that.
Here on Earth because we'd get all of that energy with none of the nasty radioactive waste that we're left with thanks to fission. But fusion requires truly ridiculous amounts of heat. That's why one of the common free energy scams over the years is called cold fusion.
So I don't know about cold fusion enough to qualify if that's like a scam or not. So I'm going to just leave this out. So, like when we studied physics, I don't remember if we talked about cold fusion at all. So, and I don't want to do any research in that. And I don't know if I should take it as a like trying to just like make a point by analogy. Hey, there is a scam that's called similarly. That's why like hot fusion is a scam as well. So yeah.
Wouldn't it be great if we could have fusion without all of that annoying heat? Sure would, but too bad. That's not the way the universe works. But there are other ways around it. And that's where this week's news comes in. Scientists have used.
Yeah, so I don't know what she means, but like other ways around it. Other ways around making cold fusion work or other ways around the scam. Like I just don't know what she means here.
Used a few different neat tricks, like the ITER project in France, which uses giant magnets to create their own miasma of plasma to fuse particles.
So I have no idea what miasma of plasma is. Is it like a song lyric or something? But basically, the idea behind those magnetic how do you call it? Basically, they're capturing hot plasma inside of magnetic field. That's because there is no material that can kind of like withstand this hot temperature, and so there is no other way to kind of like to contain this thing. And uh, I think she gets kind of like two things a bit like confused about like how magnetic forces that are holding plasma in place, like containing plasma in some configuration, how that's related to the temperature or like the energy they need to put into it. But her idea is that hey, there's like a tokamak in Europe, and here's this like laser based fusion in America. And there's actually one more. I wanted to show it as well, so I will probably do it a bit later.
At the NIF, they're trying a different tactic of firing hydrogen pellets at 200 lasers, which leads
Again, this is just a bit like sad wrong, right? So
of firing hydrogen pellets at 200 lasers.
firing pellets at lasers, so it's kind of like the other way around, but anyway.
Which leads to about 50 explosions per second, which produces heat, which is.
I have no idea what 50 explosions per second mean. It's probably, again, it sounds it sounds wrong, but I'm pretty sure the laser experiment is only working about like only working with one pellet. Maybe like the explosion happens is like in 1/50th of the second, but there is no way yet of like doing 50 explosions per second.
Is, energy. The goal of all of these experiments is to reach a Q of 1. Q is the symbol that scientists use to indicate energy gain, which is just the amount of energy you get out of a system divided by the amount of energy you put into the system.
So I think this is where her kind of like biggest point of confusion is happening. So the Q is measured by like it doesn't mean the closed system. It's not the same as perpetual motion. It's like um, if you have a flashlight and you're pressing the button and there is a light that shines. I can calculate amount of electricity that is spent and divide it by the amount of energy that I spent pressing the button. And I can measure it in Q. I can like, but does that mean anything? Is that does that prove any kind of like any free energy equation? If I turn my key in the car and car starts driving, should I be dividing like how much am I towing divided by how much energy I spent turning the key? It's kind of like meaningless. And trying to say that Q can't be more than one or like less than one or whatnot, it's like all of that doesn't make any sense. And I think in like when scientists talk about it and they're explaining how like the experiment that they're doing, like what they're measuring, it kind of like everything makes sense. But if you're trying to go into that field where she got with when you're starting to measure how towing with the car is related to turning the key, it's no, it's like it. You can get any number if you want.
So if you get 1 from that equation, that means you break even. If you get a higher number, congratulations, baby, you've got free energy.
Yeah, so this is completely wrong. This is kind of like so uh so this is a video that it was just like a few hours ago, and it actually goes into a bit more like what exactly the energy is that they were measuring. And um so it actually like here.
3.15 megajoules going out.
So this is like we shined 2 megajoules worth of lasers. So this is just basically the energy of the photons that are hitting the thing, and this is how much energy we got. This is how much energy got like expelled through the explosion. But he explains, but that this number. I mean, okay. So here are two kind of like things that I need to explain about it. So the first point is it wrong that we got more energy out of the system that we put into it? And the simple explanation is no, because apart from the energy that we spent with lasers, or like that the photons like hit the system, you're ignoring the energy that is stored in the fuel. So that's like comparing the match that you are throwing in like in a pool of gasoline, and you're saying, hey, my whole house has burned with one match. It's like, yes. If you ignore all the fuel that was already there, and if you're only counting one match and the whole house has burned, like whatever the huge amounts of energy that it requires, you're like, yes. this is what you're measuring. So this 2 megajoules is a match, and this 3 megajoules is like the whole house burning. And it only makes sense to talk about about it as a free energy if this number includes fuel. That's kind of like you had completely like empty chamber. You brought amount of fuel that has like this amount of energy, and you thrown a match, and you got 10 times the energy that you put in. That's the point that she's trying to argue, and that's the point that is like has no relation to to nuclear fusion experiments. So I don't know if I should watch further. I mean, yes, there's a point about like financing all that stuff, but this is this is where I wanted to go with this. So the simple explanation: this number doesn't include the fuel, and then you might be asking like, but what's the point then? If we're not measuring the same things, why are we even talking about? And the reason why we're talking about is that term is that nuclear fusion is so hard that we have no idea how to get energy back from it. And even if we got what is essentially is like 1% of the energy that we spent ignoring the fuel again, because this number of 2 megajoules, this is only the number that got into the fuel, that this is like the match, and we're ignoring the part where like all those lasers have to be running for some time, and they need maybe like cooling or something that you need to like produce them or whatnot. So it's like there's a huge amounts of energy that we're ignoring when we're looking at this thing. And this is because this experiment is this like nuclear fusion reaction is so complex that even achieving this it was really hard, and it took like 40 years or so, right? And so again, it doesn't mean that it's not a big progress. It's actually like really important that we did this, but my main point is like it has nothing to do with with free energy. Okay, so so I think here is where I wanted to show like this thing.
In order to achieve this,
so so if you go back to nuclear fission, so where you have huge atoms like uranium, and you want to make a nuclear reaction, idea is ideas with nuclear fission is that the most time that scientists are spending on perfecting nuclear fission is how to make it slower. But in fusion, there's basically like too much energy in fission, and the engineering challenge is to how to explode it slower. But in fusion, it's like it's so little energy going out, so we are trying to make it bigger and faster and all of that stuff. So thing is that if you have uranium or something like a fuel, nuclear fuel, it's actually doesn't require you to put like any energy. It's like a turning the key. There is such a thing as critical mass. So imagine you have uranium and you're just like putting on your table, and you're like making it bigger and bigger. Just the act of putting it on a table will cause the nuclear reaction. As soon as you have like enough material, which is like critical mass, the reaction is going to be chain reaction. You can read like you can watch on YouTube about like people who are handling uranium in, I don't know, like 50s and stuff, and they accidentally like put too much uranium or something like together, and the reaction happened, all that stuff. So it's like it doesn't require millions of lasers and like a huge like in this video he says about like the amount of energy that was needed for this experiment that was spent in a fraction of a second was like comparable to the whole US grid. I don't remember where it is, but
the sketches in comedy.
So that's not the case with the fission. As soon as you have critical mass, it will blow up. So it's actually like enough for a bomb just to have a critical mass of uranium. Just put it far kind of like away from each other, and then when the bomb drops, if the material gets together, it will blow up. That's all that you need. You just like put two halves together or something like that, and it will blow up. So then the question is, this critical mass, let's say it's, I don't remember the numbers, but let's say it's like 4 kilograms or something like that. So what if you want to make a bomb that is like 8 kilograms? You can't. You need to do like 3.5 here, 3.5 here, and then when they connect together, you get like 7 kilograms, and the reaction will start. Because if you have two halves and each of them is 4 kilograms, there will be like reaction right away. So you need to have like 3 parts or like 4 parts and so on. So the bigger the bomb you want to make, the higher the number of like parts that you need to have, and then you need to like connect them all together. So the idea then is that you have something like this, and you basically like get everything apart, and as soon as you kind of like explode everything evenly from the outside, material comes together and it blows up. But again, it's kind of like challenging to engineer it to make it kind of like bigger. That's where the hydrogen bomb comes into place. And if you don't believe in free energy, if you don't believe that you can put some amount of energy inside this pellet and get more out of this, like explain hydrogen bombs. that's the kind of like that's the principle that this experiment is running on. But basically, let's start from the beginning. So they have regular kind of like bomb, as I was showing before, that's based on uranium, plutonium, all of that stuff. And they have this kind of like chamber. Once this, basically they have a chemical explosion, like any regular bomb, right? Then it blows up and it starts this fusion reaction with a plutonium, uranium, and whatnot. And then this reaction like compresses this fuel rod, and it makes it kind of like hot enough and compressed enough so that a fusion reaction starts. And if you look into the fusion reaction that they're doing in that insist, I forgot the laser one, they're doing basically the same. They're not using like X-rays from the explosion. They're using lasers that are like compressing the fuel together and like heating it up so that reaction starts. So the idea here is that we have a chemical explosion that starts a nuclear reaction here on the top that provides enough energy that we can't get like with regular explosions, enough energy to start a fusion reaction. And if you don't believe that hydrogen bombs exist, because like they violate this free energy idea, uh, like why why do they violate it? Because the idea is that this this nuclear explosion that happens on the top, it has energy that is like 10 times less than the energy of the whole bomb is going to produce. So it's like, hey, how can we have Q of 10 if you only provide like this much energy, but we have like a huge explosion? And when I was saying it's like this uranium part, it's hard to scale it, so it's hard to make it bigger. It's kind of like limited by the amount of like the critical mass that this fuel has. But you can scale the you can scale the atomic like fusion part kind of like as much as you want because like once the fusion reaction starts, it will probably like it will probably like try to spend all the fuel that you have. Why does this system has Q of 10 and we're not calling it a free energy? Because we are the same idea with nuclear power plants, right? We are not we are not getting energy from the thin air. We are spending our fuel. We are spending the fuel that is inside of this thing in order to get energy of the fuel out. The same way as you're like burning wood or burning like gasoline, you're making a reaction that will free up some energy that is stored inside the fuel. So this is this is what you this is what you need to know about nuclear fusion. We know how to do it on the Earth. It was done, I forgot, like in 60s or whatnot. So 8 years ago. Yeah. So we already know how to do that, but we only know how to do that if we explode the nuclear bomb first, which is like huge amounts of radiation. It's completely kind of like uncontrolled, all of that stuff. We know how to control kind of like this part by itself, kind of, except for like few like Chernobyl and like all of that stuff. And we have no idea how to control this kind of like together. And what they're trying to do is they're trying to replace the nuclear explosion part with lasers. And there are like three, as far as I know, like three main methods of doing nuclear fusion. Is doing it with lasers, as this kind of like experiment does, tokamaks, as the Europe have, and I have another one. Let me search for it. Yeah, so this is the third way of producing a fusion reaction. I just heard about it like a few days ago.
Two mirrored rings of plasma on either end of a reactor, and in a 1/10 of a 1,000th of a second, they fire them at each other, sequentially activating powerful magnets to squeeze and compress the rings towards the center, where they collide, converting the astonishing kinetic energy of the ions, traveling at 300 kilometers per second, into thermal energy, raising the plasma temperature to tens of millions of degrees, hot enough to overcome the electromagnetic repulsion keeping the ions apart, and allowing them to fuse, forming new atoms and releasing a tremendous amount of energy in the process. This isn't the world of fairy tale.
Yeah, so here the idea is that we can heat up the plasma like on both ends, and then electromagnetic field will kind of like accelerate that plasma in order for it to meet in the middle, where they having like 10 or like 100 times the field, and if it's kind of like if it's collapsing kind of like fast enough, it should start the fusion. So, and again, the question is like, how do you capture all of this energy? How you make sure that your field is spent and all that stuff. So it's kind of like just a different configuration from tokamaks, and it's a kind of like completely different configuration from the lasers. As I said, lasers are kind of like more like a just they work more like a bomb. So so yeah. So as far as I know, there are like three main uh, three main yeah. So this is like the scale of tokamaks. So three main approaches to how to start the fusion reaction, and they do start it. It's just they can't capture the they can't capture the energy, and yeah. So like I don't know. First 20 years were spent to make it start. The next 20 years to get some energy out of it, and now we're waiting for like to get more energy that we spent. Yeah. So here they're saying that they're trying to capture the energy because the plasma will create its own magnetic field, and in a sense, imagine they're like spinning electric motor, and at some point this electric motor start like something happens and it starts spinning the electric motor faster, and you're like now you can capture that energy. The same because they created this magnetic field with their magnets, right? And now the magnetic field is created and they're trying to capture it with the magnets. So I mean, it sounds good. It's like no moving parts and stuff. So and they're not trying to capture like the heat, for example, which is a bit. It seems like it's a bit more prone to just like losses and stuff. So yeah, we'll see. This is this is kind of like a thing I just learned about. So I have no idea how that will turn out. So let's try to watch the rest of the video.
Last year, the NIF announced that they had reached a Q of 0.7, record breaking. And in a rather stunning leap forward, this week they announced that they had reached the break even point of Q equals 1 and even a little bit of extra energy out to achieve ignition. Holy crap, you may think. If they keep that rate up, then that means by next year we're all taking a vacation to Pluto, right? Unfortunately, no. Now, this is not a scam a la Joseph Pop, but there do seem to be some experts who are alarmingly okay with allowing the public to be confused about what Q and break even and ignition really mean.
Right. So this is an interesting point of like, why won't scientists themselves don't go out and like try to fix this confusion and try to explain that this is, hey, this is not as a big deal as you're trying to say. And I think this is actually like a valid point in this whole video is that, yeah, the scientists don't have the don't have the incentives of going and saying to everyone, hey, what we're doing is not as important as you think. You can say that the same thing about like climate change, right? So it's like, will any of the climate change scientists ever go and say, hey, we looked at the numbers again and it seems like it's not as a big deal? That's usually the argument about like those scientists are kind of like trapped in this kind of like thing. They will try to milk it as much as possible. And it's like, are the nuclear scientists trapped? Like, will they will they try to make it sound more as a big deal than it is? And I think overall scientists are behaving fine. It's just like the journalists that are trying to make it sound more exciting, and they're probably trying to do the similar video that I'm doing, right? They're trying to correct the things that are not right. But who is going to kind of like popularize that message? Who is going to share their video or like my video about this? There's kind of like no incentive to doing that. So I'm not going to blame scientists, but it's an interesting question of like, if this was a scam, will they be kind of like protesting about something like that? And overall, I think kind of yes. So I don't think it's scientists are just trying to do interesting things. They don't care about money that much. But you can actually hear that story about like why CERN was built, but like no big colliders were built in the United States. And it goes to like the anecdote of like someone in Senate asked like, hey, if we build this collider, will we find if God exists or something like that? So like a silly question, but it's like, and the scientists said no, and they didn't get any money. And it's like, are they incentivized now to kind of like lie and to make like empty promises to get money, right? So like if they would have said that they find something like God particle or something like that, well, that would have helped get the funding. And yeah, I think like more wrong things get funding and like crypto stuff or all I don't know, like Kickstarter stuff, that like there are plenty of like money that goes into useless stuff. I don't think we should be getting I don't think we should be taking away money from scientists who are working on like nuclear fusion and all of that stuff. But it brings up the interesting kind of like point, and it should make you skeptical, and you only hope that someone was skeptical and someone who knows what they're talking about, who knows physics and stuff, someone who is kind of like keeping track of this and doesn't allow to spend like too much money on completely kind of like voodoo stuff. And she said before, it's like, yeah, like patent offices don't accept applications for free energy anymore and all that stuff. So I mean, I think it's kind of like as balanced as it could be.
You see, when NIF says that they've achieved a Q of 1, they mean that the amount of energy they put directly into that hydrogen pellet has equaled the amount of energy they got out of it. The other and much more important number that you should know about is Q total. This number takes into account the total amount of energy you put into the project. For instance, how much energy did it take to turn on those lasers?
Right. So this is a bit wrong in a sense that it's again, it's like if you go back to that key ignition analogy, it's like, so Q total includes my like metabolism that I was spending when I was turning the key, but Q only measures the amount of force I was applying on the key. And like, does that change the equation? No, it's actually kind of like not important part. The important part that you should be taking into account like fuel, not the amount of energy that like when I was lighting the match, I was also like holding match and like a heavy suitcase in the other hand. Yes, my Q total is higher, but how does that kind of like explain the free energy part out of this equation. And it's just, again, it's a bit like you have to know about like how physics works to understand why this doesn't matter as much as you're trying to say. But it goes into that point that I said before about, hey, Q total is important when you're actually trying to make like a practical generator out of this, because like Q1 is not enough to make this whole project on as a generator. It's spending the energy. That's the point. It's like, unless Q is 100, unless Q total is more than 1, this is not a generator. It's just spending the fuel and spending the energy to light up this fuel. So yeah, it's kind of like it's like two wrongs don't make a right. It's like 5 levels of wrong, and we're still kind of like not at the level of where stuff actually happens.
NIF is running 192 high-powered lasers, which require a lot more energy than the 1.1 net megajoule that they produced in their experiment. To make matters worse, the energy they got out, wasn't electricity, that's heat. And if we want to use that as energy, we have to transfer the heat into electricity, and that is not an efficient process. In fact,
yeah, so again, in general, yes, but in details, kind of like no. So actually turning heat into electricity is kind of like one of the most like efficient processes that we know, because that's all that we do. Like every power plant that produces some heat and turns it into electricity, that's what its job is. And I forgot the exact number, but it's like 99% or like 97%. It's actually pretty efficient. So it's like when we're talking about like combustion engine, like in your car, that's like 35% or something. It's like way less efficient. And that's why it's like, hey, why do I need to charge my car from the grid if I can just like turn on the generator? And it's like, yeah, the smaller generator is not going to be as efficient, and like the internal combustion engine is not going to be as efficient as like a huge power plant that produces a lot of heat and turns it into a lot of electricity. So on a whole, the point is still stands, because it's like, if you're heating up like huge tokamak, how much energy are you going to lose? And if you're blowing up like this thing with lasers, how are you going to capture all the heat, because you have like tons of other things happening there? So like on the whole point is correct, but just a note is like, actually turning heat into electricity, like in general, is pretty efficient.
We'll probably lose like half of all of the energy just converting it into electricity. So while it's great that NIF hit this milestone, it's not anywhere close to being the milestone that we need to see in order to even begin to get excited about fusion as a scientifically feasible source of energy.
I mean, I don't like the scientifically feasible part, right? So because it's like, it's scientifically feasible. It's like practically feasible. It's like when it's going to turn from like a toy into something that you can actually like put on the grid and stuff. So like she trying to explain that this is like a cookie like subject, so there is like no point even trying. But there is a point. Is like she started video from like, hey, we have a sound which is like like a fusion reactor. It's like, yes, so you believe that fusion reactors work. Like, why are you trying to argue that they're not? So it's I don't like the association with like, hey, this is like scientifically impossible. No, it's pretty possible. It's like just challenging to figure out how to make all of this. It's like if you're going to like this, how do you make all the electronics that is going to like accelerate everything at the right time and all that stuff? So it's like, I don't know. Is it scientifically possible? Yes. Can we have all the proper like capacitors, all the proper like electronics to guide all of this and to make it practical? Not yet.
I mentioned that it's not a Joseph Pop-esque problem, but I do see some unfortunate connections. It's not just mainstream news outlets like The Guardian who are getting it wrong about the Q value, about what all this means. Last year, theoretical physicist Sabine Hausfeld about what all this means. Last year, theoretical
So I like the idea of like saying, hey, news are blowing everything out of proportion. It's if you're getting Q more than one, it doesn't mean it's practical yet. And that part is fine. And again, that part is pretty well covered in this video. And yes, as I said before, like scientists are usually saying kind of like normal things. I think it was like XKCD. I should probably like find it. Science are usually saying the reasonable thing, and then the journalists are trying to make it sound more crazy so that they can sell their clicks. So I agree with that part, and like general tone of like, hey, don't be kind of like too excited. This is similar to like AI stuff, right? It's like, hey, AI is going to take all of our jobs, and it's like nuclear fusion is going to take all over like energy production. No, we're not there yet. We can't dismiss all the progress that is happening, but we can't say that this is like completely solved. But I don't want to be on the side of like where you're trying to make it sounds kind of like unscientific, and especially when it's done on both sides of like journalists that don't have enough education to kind of like say things like that. Say either things like, hey, we solved nuclear fusion, and to say, hey, nuclear fusion is impossible.
Last year, theoretical physicist Sabine Hausfelder made a video in which she points out that several of the people in charge of these experiments have publicly made misleading statements about the energy output of their experiments.
Here is Nick Walkton from JET in a TED Talk referring to ITER.
ITER will produce 10 times the power out from fusion energy than we put into the machine. Now, JET holds the record for fusion power. In 1997, it got 65% of the power out that we put in. Not 1, not 10, but still getting close.
But okay, you may say, no one expects accuracy in a TED Talk.
Right, so this point about like it will produce 10 times the energy, it's actually, no, it should produce like 100 times the energy. It's not a inaccurate statement. It's actually like perfectly fine statement. It's overselling what they actually have. So it's like they don't have machine that can do that yet. They're promising it, right? So it's like they're a bit of like overselling it, but it doesn't mean that it's not a like accurate scientific thing that she's trying to kind of like to prove here.
Then listen to ITER Director General Dr. Bijot speaking to the House of Representatives in April 2016.
And I look forward to learning more about the progress that ITER has made under Dr. Bigot's leadership to address previously identified management deficiencies and to establish a more reliable path forward for the project.
Okay, the ITER will have been delivered is full demonstration that we could have 500 megawatt coming out of the 50 megawatt we will put in.
And look, I'm not inside their heads, but it's still like not that hard to understand why a person might be tempted to do that. NIF's press release includes the great news that Chuck Schumer is proud to announce today that he's helped to secure the highest ever authorization of over $624 million this year in the National Defense Authorization Act for the ICF program to build on this amazing breakthrough. That's a lot of money. Is it too much money? Is this a pipe dream that will never actually pay off? I don't know. I can't say. Personally, I would be fine with $500 million of taxpayer money going towards fusion research because we'd still have plenty of money left over for other research if we just say, stop funding the military industrial complex. Like, we're wasting money on much worse things. And I sympathize with scientists who are working on something that they're passionate about, something that could one day in the very distant future change the world for the better. But it's hard to always be able to get the general public and the funders to care about whatever your pet project is. But I don't sympathize.
Right. So far as like I can completely agree with everything she said. It's a tricky balance of like it seems like it's a lot of money, but on the other hand, it's like this is a project that requires that scale. It's kind of like it's impossible to do it on a smaller scale. It's like launching a satellite. Either you're launching it or not. It's not like you can you're not firing like 10 times smaller rocket just because you got 10 times less the budget this year. It just means that you're waiting for 10 years longer, right? So on the one hand, it's like on the one hand, when you're talking with scientists, they're saying, hey, the only way we can work on this if you give us a lot of money. And what's the solution here? Like, should we just shut it down because we don't want to give that much money? Or you're still doing that, maybe like hurting something else, or like not being able to provide something else. But usually with science, my general point is that you don't know what is going to be the successful one. And usually what happens, even if the project itself is not kind of like, is not making it, you're still getting a lot of kind of like a lot of things that are, I mean, those scientists, they're buying like paper. So you're helping is your like all the other economy and stuff. So it's like it's not completely wasted. Everything that they're doing, they're maybe like making a software to control like 200 lasers. Who knows like in when this is going to be useful and stuff like that. So this is a general argument, no matter what kind of like you're investing in. It's the same thing as like, hey, why are we spending so much money on NASA? Yeah, but then we have like internet or something. It's like something that doesn't seem like it's related. And but on the other hand, is like, how do we make sure that it's not spent on something useless? And then you have kind of like oversight, you have, I don't know, like Congress and all of that stuff, that commissions that are like checking that if it actually makes sense. And I think the idea here is that if it was completely kind of like cookie thing as she's trying to sell it, someone would have caught it. And it's like, is it practical? No. Was it practical to go to the moon? who knows? It was just like a part of the of just like arms race, right? So, but did scientists get something out of there? Yes. Could they got it some kind of like other means? Probably, right? So it's like the same thing with like colonization of Mars and stuff. Like some people are pro this, some people are against. So on the average, I don't see kind of like too much harm in that. I'm actually like really skeptical about nuclear fusion. So that's why it's so interesting for me to record this video and to provide points like pro nuclear fusion, even though I'm kind of like 100% convinced it's not going to be like a practical thing that will replace like any other kind of like form of energy. I'm actually like if I was the president of energy, right? I think the best thing that we can do is just to have more nuclear power plants that are just regular fission power plants, because they are the cleanest energy source that we have right now. And like the every year that you are not closing the coal power plant and not replacing it with a nuclear power plant, you're killing, I don't know, like 10,000 people or so. And it's like, yeah, it feels like it feels like the answer is clear. Will nuclear fusion ever be as kind of like popular as nuclear plants or coal plants? Probably, maybe like not in our lifetime, maybe never, but still, I can get through my own opinions and through my own kind of like biases and say, hey, this is still wrong. The thing that you're saying, even though in general I agree with conclusion, right? So probably you shouldn't be as excited or as invested in nuclear fusion. You still don't have to say things like it's a free energy, right? So that's why I'm doing this video. It's, you can say that I'm working against my own interest, right? So if I don't believe in nuclear fusion, why I'm recording a video explaining that it's actually like no, that's bad. But I think my mission of like, hey, let's not say things that don't make sense is more important than this particular application.
The funders to care about whatever your pet project is. But I don't sympathize with misleading people to get that funding and that attention. So sorry to once again be the buzzkill, but in my opinion, we aren't anywhere near to achieving fusion energy as of right now. But again, not my field, out of my depth. So if you happen to be a physicist who knows what you're talking about, not just a physicist, I play a physicist on the internet. If you're actually a physicist, feel free to comment below. Tell me why I'm wrong about this, that.
Yeah, so this is what I'm doing. I got a bachelor degree in physics. I almost got my master's degree. I kind of like flanked last, like, basically like 2 weeks of the whole degree, and I was getting physics degree in Earth physics, so it's more about like how Earth and Sun are kind of like Earth, Sun, kind of like magnetosphere and all that stuff. So it's not kind of like directly related to any of this like reactions, right? But we got enough kind of like just education along the way, so for me to at least know like this kind of like basic stuff of we all got our lectures in thermodynamics and like the perpetual motion machines. So this is I feel like I'm qualified enough to talk about this at least.
We are on the brink of a free energy revolution, but I remain skeptical.
Yeah, so I I think that my main thing that kind of like rubbed me the wrong way is this kind of like guilt by association of like, hey, there are scams. There are people who are saying that they can get stuff out of thin air, and the way that papers show nuclear fusion, it sounds a lot like those scams. So papers are wrong, and you're wrong taking it that way of like trying to put it into the scam territory. Papers trying to make it kind of like sound fantastical, even though the practical limitations, like I agree with everything about like practical limitations, yet I don't see the nuclear fusion in the same way as like free energy scams, as getting stuff from the thin air. And the main thing is that it is spending fuel. It's not it's not catching some kind of like cosmic rays. It's not getting energy out of ether. You're spending the fuel. Each time the explosion happens, you need to put a new pellet into it. So that's why it's so confusing, because Rebecca's saying, hey, they're firing lasers at the pellet. Hey, they're using like this fuel. And then she kind of like completely ignores the fuel part. And it's like, why did you say it before then? It's like, you know that there's a fuel, but now you're saying about like now you're saying that getting Q more than one is somehow kind of like controversial. It's not. The energy that you're putting with lasers is basically like energy of the match, and you hope that this energy is actually kind of like negligible. You hope that you are getting so much energy out of your fuel that the part where you the part where you lighting up the match is kind of like completely irrelevant. But because how hard this problem is, it's actually not yet irrelevant. It's actually in the same kind of like ballpark, right? So it's like 2 megajoules, 3 megajoules. It's like we're kind of like we're still not perfected this enough to make it into like a real practical thing. But if you're trying to make an argument for energy from the thin air, you have to calculate the energy of the fuel. Otherwise, it kind of like doesn't make any sense. It has to be a kind of like a closed system. If you put a fuel first and you don't count it, it's like, what's the point then? It's like it's not against any like laws of thermodynamics if you just ignore the part that you don't like. Yeah, and I hope my explanation was this. That's where kind of like my mind went. Is like, hey, we have this thing. We're just using like explosions instead of lasers, and it works. It can level the whole cities. So like, why are we talking about this as if it's something like impossible? Anyway, so instead of like conclusion, watch this video, and I think he provides like a few more sources about like stuff that you can. I think at least he like mentions this. Maybe it's not in the description, but he mentions like a few more sources that you can read more about it, like in science circles, not just from journalists. And yeah, and I don't have any kind of like bad feelings for this video. It's not the first time where I kind of like disagree with stuff that she's saying, but hey, she wanted a discussion, and she's getting a discussion. I feel like that's a right approach here. Okay.